All right, so now we're going to be looking at the second question on the 2026 AP Physics 2 exam and the free response section. And so here we have energy levels and the corresponding states for a hypothetical atom. We have three of them, n equals 3, n equals 2, n equals 1 states. And on the figure, we're asked to draw arrows to represent all possible transitions that could result in the emission of a photon. So in order to emit a photon, we need to go from a higher energy state to a lower energy state. And because this is the Bohr model of the atom, we can only jump from one energy level to another. And so if we start at the n equals 3 level, we can go down to the n equals 2 or the n equals 1 level. And then we can also transition from 2 to 1 as well. Perfect. And I think that answers part A. For part B, derive an expression for the wavelength of the highest energy photon that can be emitted from the atom. Express your answer in terms of E naught and physical constants as appropriate. So it seems like the highest energy emission is going to be from n equals 3 to n equals 1 state, because that'll be the largest change in energy for the atom. So we'll start that here. So the change in energy of the atom should be from negative 5 E naught as the final state minus negative 2 E naught as the initial state, which will give us a change in energy of negative 3 E naught, which means our photon, in order to conserve energy, must have an energy of 3 E naught. And we know from the formula sheet that the energy of a photon is equal to the Planck's constant times frequency of that photon. And so we should have 3 E naught as the energy equal h times the frequency. We also know that photons travel at the speed of light. So we can set their speed equal to wavelength times frequency. Therefore, the frequency expression should be the speed of light divided by the wavelength. We'll substitute that here. And so therefore, the wavelength should just be Planck's constant times the speed of light divided by 3 E naught. I think that answers part B. Now on to part C. We have a device that can emit monochromatic electromagnetic radiation. The wavelength lambda of the radiation can be varied over a continuous range of wavelengths. On figure 2, sketch the energy of the emitted photons as a function of lambda for values between lambda naught and 4 lambda naught. Photons with wavelength lambda naught have an energy 4 E naught. Perfect. Okay. Sketches made in the shader region will not be scored. So I'll move on to figure 2. So we definitely know that wavelengths of lambda naught are 4 E naught, so that point should be on our graph. From before, we know that the energy of a photon is equal to h times the frequency, which should be Planck's constant times the speed of light over the wavelength. So we should have an inverse relationship. As the wavelength increases, the energy of the photon decreases because the frequency would then decrease. And because it's an inverse relationship, we know that we're probably going to have these values as well. So doubling the wavelength cuts the energy in half, and then quadrupling the wavelength should cut the energy down by a factor of 4. So our sketch should probably kind of go through those points. All right, I think that's it for part C. All right, part D. A student claims that based on the energy states shown in figure 1, the atom can emit a photon of wavelength lambda naught and energy 4 E naught, like the device described in part C. Indicate whether the claim is correct or incorrect. I believe it's actually incorrect because we saw in part B that the change in energy of the atom was only 3 knots. Incorrect. The most energetic photon the atom can emit is from state n equals 3 to n equals 1, which would have an energy of 3 E naught. There is no pair of states that could emit a photon of energy 4 E naughts. I think that is it for part or for question two.